Let's try our first example of Newton's second law. A toy car with a mass of 0.8 kilograms accelerates on a frictionless track. It's pulled by a string with a force of 1 Newton to the right. Draw a free body diagram of the car, determine the value of all forces, and calculate the car's acceleration. So I'm going to start by drawing the car. Here's our toy car that's being pulled by a string to the right with some force. If it's a string, we can call that tension. And then I'm going to identify the other forces on the toy car. It's going to be pulled down with a force of gravity, and it's going to be supported by the track, right, with a normal force. Okay, and then I'm told to determine the value of all forces. So first, let's start with the force of gravity. If you want to go from a mass of kilograms, 0.8 kilograms, to a force in newtons, on the Earth, the relationship is just mass times 9.8, okay? If you're trying to figure out the force of gravity on a different planet, then you'd multiply by the acceleration due to gravity on that other planet. So I'm going to find this by taking the car's mass of 0.8 kilograms and multiplying by 9.8 meters per second squared. So the force of gravity is specifically 7.84 newtons. Well, it stands to reason that the normal force will be the same because the car is on this level track. We can assume it's not rising or falling and that it will be vertically balanced. The forces will be vertically balanced. Okay? And then we're told that this force of tension is 1 Newton here in the problem. All right, I have now determined the value of all forces. Now it's time to get the acceleration. So first, I want to determine the net force. The net force, okay? As a reminder, the net force is the sum of all forces. So this force vertically, the normal force upwards and gravity downwards are equal and opposite. So the net force in the vertical direction is going to be 0. And if I focus on the horizontal forces, I've got 1 Newton of force to the right, but nothing to the left. And so my net force is going to be just this 1 Newton to the right. And oftentimes I like to draw the net force with a separate block arrow. And in this case, I'm going to draw it just down here to help me visualize the net force. This is not a separate force. It's not a new force that goes on the free body diagram. It's just the sum of all the forces. And so I'm going to identify this as 1 Newton to the right, okay? So now from Newton's second law, the acceleration is just the net force divided by the mass, okay? The net force is 1 Newton to the right. The mass is 0.8 kilograms. So be careful. A lot of students will just throw this in, right? They'll say, oh, the force of gravity. But Newton's law is looking at the mass. So we're focusing here. And then calculating that out, I get 1.25 meters per second squared. And then that has a specific direction. The direction will always be the same as the direction of the net force. So that's going to be to the right. The car will accelerate to the right. Let's try another example. A firefighter of mass 80 kilograms slides down a vertical pole with an acceleration of -4 meters per second squared, right? Sliding downwards, accelerating downwards. The pole does provide friction. Draw a free body diagram of the firefighter and determine the value of all forces, okay? So I'm not, super good at drawing firefighters, so I'm going to draw just a stick figure. Here's our firefighter that's sort of holding on to a pole. I'm not going to draw the pole, right? Because in free body diagrams, you just focus on the object, you erase the environment, but you replace any of the forces that the environment is putting on the object. So let's start with force of gravity down, 80 kilograms times 9.8 meters per second squared. So the firefighter's weight is 784 newtons. There is going to be a force of friction upwards on the firefighter, because as the firefighter slides down, friction opposes that motion, but I don't know what that force of friction is. Okay. And I am going to find out the force of friction by getting the net force. Okay. So let's first do this. Find the net force. From Newton's second law, the acceleration is the net force divided by the mass. The acceleration is -4 meters per second squared. The net force is my unknown. The mass is 80 kilograms. Okay? Multiplying both sides by 80, I get that the net force is -320 newtons. Now, what's the negative all about? Well, that means it's down. So over here, I'm going to add my net force block arrow to show that it's 320 newtons in this direction, right? I'm not going to draw the negative here because the arrow is already being drawn down. Okay, now that I know the net force, I can figure out the force of friction. And this is how I would do it. I know that the forces have to add up to 320, meaning that friction upwards minus gravity downwards will be equal to -320, because that's the direction of the net force. So according to the free body diagram, and I'm running out of space here, so I'm going to draw this up here. According to the free body diagram, the net force will be equal to the force of friction minus the force of gravity, right? Force of friction is up, gravity is down. So the net force is -320 newtons. The force of friction is my unknown. The force of gravity is 784 newtons. And so the force of friction is going to be 464 newtons. And I can put that right here. Now, if I wanted to back calculate, I would say, okay, well, according to the picture, 464 up minus 784 down should lead the net force to be 320 down, meaning that according to the net force of 320 down, this side should be 320 greater than this side, and it is.